This is a Module 5 video introducing catalytic cycles in metal-catalyzed reactions. In the Module 5b videos, the concept of catalytic cycles will be introduced in the context of catalytic hydrogenations. In the reading, Chapter 12 is a review of thermodynamics and equilibration. Chapter 23 briefly mentions catalytic hydrogenation, but in less mechanistic detail than we will explore here. Chapter 40 presents some of the individual mechanisms that are involved here, and then Chapter 41 shows an extension of rhodium-catalyzed hydrogenation with chiral ligands on rhodium to favor enantioselective hydrogenation. Wilkinson's catalyst, chlororhodium tris-triphenylphosphine, was reported by Wilkinson's laboratory in the mid-1960s. It was one of the first organometallic catalysts that was shown to be soluble in organic solvents, and in the intervening decades has proven to be extremely useful. One of the benefits of using a soluble catalyst, such as Wilkinson's catalyst, is that these catalysts tend to have better selectivity for alkenes that are more electron-rich and less sterically hindered. This substance is called carvone. It has two alkenes. The cyclic alkene is in conjugation with the carbonyl group, which lowers the LUMO energy of that alkene relative to the acyclic alkene. The acyclic alkene is also disubstituted and is less sterically hindered. With Wilkinson's catalyst, we observe high selectivity and an excellent yield. The other advantage is that this works with 1 atmosphere of hydrogen, whereas many other hydrogenations require high-pressure hydrogen, which has substantial safety hazards associated with it. Geoffrey Wilkinson won a share of the Nobel Prize in Chemistry in 1973 for this and other discoveries, most notably the structure of ferrocene, which shows up on page 1072 of the textbook, but will actually not be covered in this course. More recently, Wilkinson's catalyst played a supporting role in the Nobel Prize for Physiology or Medicine. Avermectin is an antibiotic which was discovered in soil by a microbiologist by the name of Satoshi Omura. This compound has anti-nematode activity, meaning it kills worms. Upon hydrogenating one of the alkenes to ivermectin, this is a much more potent compound against worms, especially the worms responsible for river blindness, afflicting millions of people. And this discovery was made by a group at Merck Research Laboratories at Merck Pharmaceutical Company, headed by William Campbell. These two men shared half of the Nobel Prize in 2015, which was shared with Tu Youyou, who is responsible for discovering an anti-malarial drug. Continuing with the worksheet, this shows the accepted mechanism for hydrogenation of alkenes catalyzed by the Wilkinson's catalyst. This mechanism has been well established because each one of the intermediates has been characterized and is demonstrated as active within this catalytic cycle. We'll work through each of these steps systematically. But for review, let's begin with Wilkinson's catalyst and discussing what is its formal oxidation state, how many d electrons are in Wilkinson's catalyst, and what is the total valence electron count in Wilkinson's catalyst. Turning to the next page of the worksheet where we will discuss step 1, I'd like to continue the discussion in class with the name of the reaction in step 1. It's one which has already been introduced. And what is the total valence electron count of the product from step 1? Moving to the bottom of this page, step 2 is called oxidative addition. This was mentioned in passing in chapter 9 when you studied the Grignard reagents, but it was not described in detail. The mechanism involves an additional detail that I did not show in the catalytic cycle. There is a ligand association step where the electrons from the hydrogen-hydrogen sigma bond are donating to an empty orbital on rhodium. And then the second part of this is the oxidative addition. 2 electrons come from the hydrogen-hydrogen sigma bond to form a rhodium-hydrogen bond. 2 more electrons come from a d orbital on rhodium to form a second rhodium-hydrogen bond. At the top of page 3 are a few questions to discuss in class. Specifically, for the product of this step, what is the formal oxidation state of rhodium? How many d electrons are there? And what is the total valence electron count? To conclude the section on oxidative addition, I show a couple of the structures from page 2 of the worksheet with the note about oxidative addition and reductive elimination. That is on page 3 of the worksheet. Oxidative addition and reductive elimination are the microscopic reverse reactions. These 2 steps are in equilibrium, with the equilibrium affected by the concentration of the reactants leading into this step, as well as the reaction of the product from this step. Step 3 is shown lower on the 3rd page of the worksheet. So in class, we'll discuss what is happening in this step, and we'll follow up with determining the total valence electron count of the product of step 3. This concludes the first video of Module 5B.